Hi, I'm Kason Klarman, and this is my Motion of a Falling Object Lab report for Physics 1. The purpose of this lab is to demonstrate the motion of a falling object and compare the actual data to what we have calculated in class. After we finished our experiment, we concluded that drag force is much more noticeable at high velocities rather than negligible. In this lab, we used Newton's second law to find the acceleration of the eraser. Then we used the velocity update formula and the position update formula to model and graph the experiment. We assumed that the only forces acting on the system were the drag force and gravity, which we modeled with the force of gravity being equal to mass times the gravitational acceleration in the negative y hat direction, which we decided to be downwards, and drag being b, which is the drag constant, times the magnitude of velocity squared in the positive y hat direction, which we decided to be upwards. For our graph data, we assumed that each point in tracker was perfectly placed in the center of the eraser, and that the eraser was dropped with a perfect zero velocity. For our experiment, we declared the eraser to be our system, and everything else to be the surroundings, such as the earth and air. For our procedure, we held the eraser above the ground, then dropped it, filming the drop for the data which we put into tracker. For our calculated data, we created two different models. One with the drag force and one without. For both, we used the velocity and position update formulas to calculate the positions. I decided to remove mass from the FNet code because it did not have any effect on the final velocity. We found the value of b in the drag to be 1/2 c rho a, which we found to be 0.00169764. Here in the code is our FNet vector with no drag, where we have g in the negative y hat direction. Here we have the velocity update formula being multiplied by the acceleration in delta t, and the position update formula with the new velocity multiplied by our change in time. Here we found the FNet vector to be the gravitational force plus the drag force, which we found as the negative acceleration due to gravity and the positive acceleration due to drag. Finally, we put all of the graphs onto one, and we can see that as time increases, the actual observed position becomes closer and closer to the gravity with drag rather than the gravity without drag. Therefore, we can assume that drag was affecting the results of our observed data. Finally, our what-ifs. As we can see with the curve at the end of our velocity versus time graph from our modeled experiment with drag, we can see that it predicts a terminal velocity as the curve starts to flatten out by the end of this. We can assume at this terminal velocity that the force of gravity has to equal the force of drag, therefore the FNet would be 0 and the velocity would be constant. Even if the ball has some velocity at terminal even if the ball had some initial velocity, the terminal velocity of the object will not change, just the time to reach the terminal velocity would change. As you can see, it would just be starting at a different v1 versus v2 as I put on the graph. Simply the object would just start at that lower spot. Thank you.